other test areas where there are high mountains, where there's more vegetation, just to see what exactly is going on and what are the best parameters to generate these DMs. So just a bit more context, the event was in the 30th of December 2020. There were some minor events after that. 10 people lost their lives, several buildings were destroyed, several people evacuated, and then more to the data itself, it had a detachment area of 0.12 square kilometers, an outlet area of 0.26 square kilometers, 1.35 million cubic meters were mobilized, and almost 1 million cubic meter was also deposited. The study area is here in Gjerdrum, Norway, closer to Oslo. And this is one of the images that my coworker got when he went to the site to take a look at what was happening. This is a bit of a aerial view of what was the before and after. Luckily, because this was a big event, we have a lot of data where we can check what was going on. A lot of UAV imagery, so like reference data to see what how good our DMs are getting. And we have here the elevation difference, so what was detached, what went out of the landslide, and here the deposition, what was deposited after the event. So let's go step by step on how this workflow will work. Step one, before having the workflow, would be to query data. If you've ever queried data from the Alaska facility, you will be familiar with these screens. So first what you do is draw an AOI, and then you get a bunch of images in this area here that correspond to the area that you're looking into. Once you're done with that, this can also be by temporal search, just narrow down. Once you're done with that, you will have to do a baseline search, meaning that for every image that you found, you will need to find a pair that is compatible with the image that you selected, so that you can do this double pass with the imagery. So having a small temporal baseline, good perpendicular baseline, and that they are both in the same orbit, that they're both in the same path, so that they have these characteristics needed to do interferometric SAR. So this is how you would do it normally. And this is what we did to improve the workflow. In what way? If you would do this manually, you would have, for example, for this example here, we have the AOI, we have 2 months. So we start in July, 1st of July, and we end on the 31st of August. And if you do this manually, you will get 59 geographic matches. So you would have 59 images. For each image, you will have an average of 355 images that you have to look into if they match or don't match. That means you will have to look into 20,986 matches. And then from there, you would have to filter how many you really want. In this case, it's 86. So with this first step, I simplify this in a way that this will all be done in the background, because I queried the Alaska API, where you will just get a list of your reference ID, your match ID, the orbit, the path, and a temporal baseline, perpendicular baseline, reference dates, everything that you need. You don't need to spend all this time querying for the data. That's the bottom line. That's what also my coworker was taking weeks to do. Now she's very happy. She can just run it once, get the CSV, and see what's going on. What I added also is a URL to the EO browser of Sentinel Hub, so that you can take a look at how it looked exactly around these dates in optical imagery, so that you see, okay, actually there was snow on these dates, so it's not so useful for me to do interferometric SAR because there will be too much interference with my final workflow, or there was a lot of clouds, maybe it was raining too much, maybe the atmospheric is not going to be the optimal to do my interferometric SAR, so you can also choose here. From here you can take a look at how everything is going. Then you download, and that's very simple. You just have the CSV, and I put here a column where you, as an analyst, will have to change from false to true. And with that, you just pass this to the next script, saying, okay, everything that is true, please download it. It will take time. Sadly, we have to download the whole image, because otherwise Snap will not be able to process this. It is a bit of a quirk, but okay, that's what we need to deal with. And if you have a server, this will go much better in the batch download. And step number 3 is generating the DMs. This is how let's call it, you would normally do it. This is the interface of Snap. It's, yeah, I'm not so used to it. I don't really like it. I don't know how to do all the visualizations and check everything, but this is somehow how it looks like. And I will not go through all of this, but this is every single step that you need to do to get a DEM out of it. So it's quite long. It's divided in 3 pipelines because these can all be done in one go, but then you need to get out of this Snap environment to another software to do this very specific phase unwrapping. And then you need to go back to Snap and finish your last steps, which would be doing this DEM, terrain correction, etc. So the idea here is that everything was bundled into one script. So the next one that will go, you can give a lot of parameters that you would normally give to Snap. You can give them to the script. And so that you don't get lost into, okay, what did I set here? Why did I didn't set here? I created a log file where you will have all the information of, okay, what did I set? What were the parameters that were computed inside? So like the subset, the burst, the swats. You have a lot of parameters for each pipeline. And we have some information that is also computed during the process. As you see here as well, you have some outputs already. Just to give you an idea, my coworker would spend like at least 3 days generating a DEM. Now this is done in half an hour. So it's quite useful. And we also have these intermediate steps because it's very important when you're doing a DEM to look at the intermediate products and see, okay, is this really working well or not? Is the interferogram making any sense or not? Do we have any errors or not? So this is how the products look like. We get elevation, we get the coherence, which is how matching are the 2 images, just to see how good the elevation values would be on each of the areas. So higher areas means there is a better match between the 2 images. As you can see, this is not a great match, but this is one of the examples that I chose during this. You can also have an elevation filter by a coherence threshold. If you think this coherence is just too low, you can just get rid of this. And we have intensity, the phase, and the unwrap phase. Finally, thank you. We have step 4, which is assessing the quality. And the idea here, I added another little script where you can get some reference data. So that this is where the open topography enters. You can download the NASA DEM or any DEM that is available for your area. And also the ESA world cover, where you can do some analysis by land use land cover and to see, okay, where is my DEM elevation performing better or not. And I use for this very good package called XDM. So if you have also working with DEM data, I recommend you looking into it. I would recommend you do your own quality assessment using this package, but because we're trying to do this in several steps in organized way where we just generate several DMs and assess them all in a row. That's why there's a module for doing a quality assessment. And this little bit of a hint of what you can get out of it. So for example, we have the reference DM. In this case, is the NASA DM. This is the Sentinel1 DM. So you can see it is very patchy. It's not super beautiful. But okay, this is one of the things that we get. And what we do is get an elevation difference to see, okay, where are these values performing better or not. So as you see, this area is quite bad. But the area that we're really interested in is the landslide. So this is what we focus on. It's still bad, but not as bad as the other areas around. And as you see, you can get some information about how the qualities, the error, how it's changing according to the slope. So higher slopes have higher errors as normal because then the angles are harder to compute. We also have some information about how it varies with the aspect. And because we included some land use, land cover data, we can also see, okay, with grassland and cropland apparently is doing okay, but with tree cover and shrubland, we have a bit more problems. And just to get a general idea, I've also included these terrain derivatives where you can have a quick look of how it would look like if you're really working with this DM. So just for comparison here, this is the NASA DM, so a bit nicer. This is the Sentinel1 DM, very noisy, but still, you can get a general idea of what you're working with. And of course, the vertical co-registration, as I said, if we have a reference DM, we can see, okay, how is this looking? Is this looking good or not? Some statistics that you can get as well to see, okay, how is the error good or not? And finally, calculating volume. So if you have a pre-event and a post-event, you can see, okay, what was the volume that was changing between these two timestamps. And you have the elevation difference and some of the numbers that you get that here we can compute. This is really an overestimation of this particular event, but alas, this is also meant to do a systematic analysis of all the DMs that we want.